Thank you for the introduction, and let me check if you can see the slides in presentation mode. Yeah, great. Uh, Again, thank you for the introduction, Professor Lee, and thank you for inviting me and recommending uh, to have a talk in the symposium. Um, and thank you for attending, everyone. And as introduced, my name is Joowon Lee, and I'm at Control and Dynamic Systems Laboratory at Seoul National University. And technically, I am a PhD candidate, but I'm going to graduate at the end of this month. Anyway, today I'm going to talk about design of controllers having integer coefficients for encrypted control, and please feel free to interrupt me anytime with questions by turning on your mic. So here are the contents of today's talk. As this is the title of this talk, I'll first briefly introduce what encrypted control is, and then I'll explain why we need controllers having integer coefficients in the context of encrypted control. And then I'll introduce our recent research on the existence of a stabilizing controller having integer coefficients and how to design it. And next, I'll explain how to convert a given controller to have integer coefficients. And these two are recent results from a collaborative work with Professor Dongil Lee of Incheon National University and Professor Junsu Kim at Seoul Tech. So let me explain the concept of encrypted control. Uh, by the way, can you see the whole screen or is the Zoom video hiding it?
The full screen, at least
Yeah.
from my end. All right.
Okay, thanks. Uh, so to enhance the security of cyber physical systems, we can make use of encryption and apply it uh, to some control system. And in a naive and conventional way shown on the left side, uh, control data are encrypted before transmission and decrypted just after arrival. And but uh, this method protects the control data during transmission, but it cannot protect them during the control operation. And also, control parameters of this controller are exposed. On the other hand, in this encrypted control system on the right, the encrypted controller operates directly over encrypted data, so the control parameters are hidden and the control data are protected throughout the whole cyber layer. And the decryption only happens at the actuator. So to implement an encrypted control system, we use a type of crypto system called homomorphic encryption. Homomorphic encryption enables direct operation over encrypted data. For example, when we have plain data A and B and their encryptions, both A and both B, homomorphic encryption allows operations over this both A and B like this, that and the results of these operations correspond to A plus B and A times B when they are decrypted. And homomorphic encryption supports addition and multiplication over a finite set of integers, which means that these plain data A and B belong to a finite set of integers, and other operations are very expensive for real-time control operation. Also, errors can accumulate through recursive operations, and these kinds of properties cause some major issues when implementing uh, controllers over encrypted data. So encrypted control addresses these kinds of issues by combining control theory and cryptography. And since, as I mentioned, homomorphic encryption supports addition and multiplication over a finite set of integers, even encrypting a linear dynamic controller is not trivial. Let's think of a given controller like this, where Y is the plant output and U is the control input. And the first step we need to take is to reformulate this given controller using addition and multiplication over a finite set of integers. And the next step is to encrypt them by homomorphic encryption. Specifically, um, what I mean by a finite set of integers is in many cases given as this ZQ as a space of plain data. And here Q is some very large positive integer, and you can see that ZQ is bounded. And uh, operations, addition and multiplication over ZQ is defined using the modular operation. And this means that when A plus B exceeds a certain bound, like this, and then the outcome of the addition over ZQ will be some value that is chopped off. So let me show some naive way to reformulate this linear dynamic controller. First, the initial state of this controller, which is a real vector, should be quantized using some scaling factor. And one approach is to quantize each control parameter, each matrix, using a scale factor S2, and then multiply it to the quantized state, initial state. And then the result will be approximately this value, which is of scale 1 over S1 times S2. And at the next time step, we again multiply this quantized state matrix F, and then the scale will grow like this. So now you'll notice the problem, because as time goes by, uh, the scale of the quantized state will exponentially grow and eventually overflow the space of plain data ZQ. And then, as I said, when this value overflows ZQ, uh, because of the modular operation, we'll have a, a chopped off value, which is different from what we expect. And another approach is to scale down this quantized state at each time step by multiplying this scale factor S2. However, multiplying S2 means that we actually divide this value by a large integer because of this. But uh, as I said, division is unavailable, um, almost impossible because of its computational complexity. So these approaches will not work. And that's why we need the state matrix F to be an integer matrix. When we have the F as an integer matrix, we don't need to quantize this matrix, so we can reformulate this given controller like this one. And then by this quantization method, we can the scale of the quantized state and the outcoming control input are consistent. So This is what we call the need for an integer state matrix. Well, still, there are previous approaches without reformulating a given controller to have an integer state matrix. However, they all rely on some additional or external resources. For example, they require some extra communication between the plant and the controller, or others use the bootstrapping technique, which is a technique from cryptography that requires a huge amount of computation. And there's also a result using a periodic reset of the controller. So let's go back to controllers having integer state matrix. Um, there are previous approaches to design such a controller or convert a given controller to become to have this kind of property. However, many of them are applicable only for a restricted class of plants, satisfying, for example, the strong stabilizability or other uh, other technical conditions which are presented in these papers. There are still methods that work for any plant or any given controller, but they use some special measures to do so. For example, there's a technique called re-encryption. But it requires an additional input channel to the controller and plus some extra communication link between the plant and the controller. Or uh, any given controller can be converted into some new controller having an integer state matrix, but with a time-varying implementation. This means that the resulting controller will be a time-varying system. And here comes our main result. We have shown that for any discrete time single input, single output LTI plant, there always exists a stabilizing controller having integer coefficients. Here I use the term having integer coefficients, and it is defined like this. A transfer function has integer coefficients if it can be expressed as a fraction of polynomials where the denominator polynomial is an integer monic polynomial, which means that every coefficient of this polynomial d is an integer when the leading coefficient is 1. So we don't say that a transfer function has integer coefficients, even though uh, we don't say like that when the leading coefficient is not 1. And it can be easily shown that this the property of having integer coefficients is equivalent to having a state space realization with integer state matrix. And I would like to emphasize that until recently, the existence of a stabilizing integer coefficient controller has been shown only under some sufficient conditions. And we also provide a constructive method that I'll show later to find such a controller. And here is the formally stated problem. Given a plant P, find the controller C such that first, the closed loop system is stable, which is equivalent to um, this polynomial, this closed loop characteristic polynomial being a sure stable polynomial, which means that uh, this polynomial has all its roots inside the unit circle. And second, the denominator of the controller transfer function is an integer monic polynomial. And without loss of generality, let the denominator and the numerator of the planned transfer function are relatively coprime, and also dp is a monopolynomial. And uh, the we also let np has a non-zero constant term, and otherwise, we can slightly modify our solution and yes, also have the stabilizing integer coefficient controller. So this is just for simplicity. And with these conditions, uh, we can restate the problem in terms of polynomials. Given polynomials dp and np, we aim to find polynomials dc and nc such that this polynomial is a sure-stable monopolynomial. And second, DC is an integer monopolynomial. And there's a third condition. The degree of NC should be less than that of DC. And this is just for causality of the resulting controller. And please note that the resulting controller, uh, NC over DC, can be of any order. It just uh, needs to have integer coefficients. And our key idea to solve this problem is to update the polynomials DC and NC. So specifically, let this closed loop characteristic polynomial be gamma. Let us just define gamma to be this closed loop characteristic polynomial, and we want to uh, we're going to update these three orange colored polynomials through iterations until DC becomes an integer monopolynomial. So first, we initialize this DC and C and gamma by solving a classical stabilization problem, so that gamma is a sure stable polynomial and uh, the degree of NC is less than that of DC. But of course, solving a classical stabilization problem wouldn't lead to DC being an integer polynomial. So we take the iteration step. At each iteration, we choose a sure-stable monopolynomial R and multiply this R to both sides of this equation. And then by adding and subtracting this part with some polynomial W, we have this equality. And then we update DC to be this part and NC to be this part and gamma to be R times gamma. And then, of course, since we chose R to be sure stable, the next gamma, gamma plus, is sure stable. And with some degree condition on W, the degree constraint is also satisfied. However, it doesn't ensure that the next DC is an integer polynomial. So, let's have a closer look to this uh, update of DC. So I just rewrote this part again, and R is of our choice, and DC is the current denominator of the controller, and DC plus is the next denominator. And let R be a degree n sure stable monopolynomial, where n is the Platt order. And let's add some update rule that DC can always be expressed solely by n number of coefficients, which means that DC DC can be expressed as a multiplication of some degree n monopolynomial A times some monomial. And then DC can be expressed by solely by the coefficients of this polynomial A. And that also holds for the next DC, DC plus, and here we have A plus instead of A, which means the next n coefficients of DC. And since R is a degree n polynomial, and it is multiplied to DC, um, the degree of DC has increased by a small n. Here, this large n is just some non-negative integer, and it'll be changed through the iterations. So with this additional constraint, let us just rewrite this upper equation, and then it results in this equation. And now our interest is how to choose R so that this A becomes an integer polynomial. And we have shown that given the current A and our choice of R, uh, the next A satisfying this equation for some polynomial W is always uniquely determined. And when A plus is determined, W will be automatically determined. So now our focus is on the relation between this current A and our choice of R and the next A. So our next idea is to express this update of polynomials uh, over some as a dynamic system over Rn, like this. So here, A corresponds to this vector x, since vector x just consists of the coefficients of polynomial A, and that also holds for x plus. And here, U is a vector of coefficients of Rz. And here, the matrix delta x is defined from the vector x and the coefficients of NP. So now we have a dynamic system with state x and input u. And that makes sense because our current polynomial A is the state and u is of our choice. And since we need R to be a sure-stable polynomial, we need some constraint on this input u. And we use a property that R is sure stable if the one norm of U is less than 1, and which holds by the Rouché's theorem. So now our goal is to move the initial state x0, which is determined by the initial DC, move the initial state to an integer vector x star using a bounded input U within a finite number of time steps. So our iterations should end in at a certain point uh, to to result in some integer coefficient controller. So moving the initial state to an integer vector should be achieved within a finite number of time steps. Now, the next key idea is to actually reach an integer vector within a finite number of time steps. So to this end, we have derived the useful property of the matrix delta x, which is that delta x is invertible if and only if the polynomial made up of uh, the polynomial made up of the elements of x and np are coprime. And we want x to be uh, we want delta x to be invertible because as I'll show later, we're gonna use the inverse of delta x. So first, we determine spaces where delta x is singular, the spaces we need to avoid. And these spaces are represented in hyperplanes like these blue shaded parts of this figure on the left. And we want to move the state x along with the line segment between x0 and x star, like this. And we want to avoid the hyperplanes, so we select an integer vector x star so that this line segment does not cross any of these hyperplanes. And we have shown that such integer vector x star always exists. And the final step is to design a bounded input uh, that has its one norm less than one, uh, and it is designed like this. So it obviously is bounded, and here mu is just a parameter, design parameter. And this input just moves this x along this line segment. And we have shown that with that previously shown kind of control input, the with any given initial state x0, the state will reach x star within a finite number of time steps, which is bounded like this. So this means that our update algorithm of the polynomials um, will end within a finite number of iterations, and for any given plant NP over DP, we'll have a stabilizing integer coefficient controller. And for the complete set of algorithm, see our paper on arXiv, which can be accessed by this QR code. And now I'll show some numerical example. Let's just consider a discretized and linearized inverted pendulum as the given plant. And by and through our proposed algorithm, uh, the resulting controller looks like this, which clearly has integer coefficients on its denominator. And yes, this controller actually stabilizes this plant. And as you can see, this controller that stabilizes this fourth order plant has order 8. And as you have already noticed, our update algorithm increased the order of the controller by n at each iteration. So the algorithm usually produce a high order controller. And one may question the practicality of this algorithm to design an integer coefficient controller. And yes, we have kind of solution to that kind of issues um, by using ring LW along with ring GSW scheme. And this is just the name of a type of homomorphic encryption. And these kind of homomorphic encryption schemes use a polynomial ring, um, a set of polynomials as a space of plain data. So the plain data is a polynomial, not a single integer. And this enables packing of multiple integer messages into a single polynomial, which means that we can encode several multiple messages and pack them into a single polynomial. And it also enables faster recursive homomorphic multiplications. So these papers, uh, which I'm also part of uh, consider use ring LW plus ring JSW scheme to efficiently implement encrypted controllers and analyze their performance. And we actually we actually encrypted the eighth order controller here, this one, using the methods of these two papers. And the result was like this. So here, this table shows the elapsed time for the whole encrypted control operations at each time step. And particularly using the method of this second paper, the elapsed time was in average less than 5 milliseconds, which we think as fast enough. And we used a homomorphic encryption library called Latigo, and it our setting also ensures the 128-bit security, which is kind of a standard in this cryptographic field. And here I posted the GitHub link for the implementation of this controller. So I think even though our proposed algorithm produces controllers of high order, we can leverage these kinds of methods to efficiently implement the actual encrypted controller. And now the remaining content is conversion of a given controller to have integer coefficients. So the problem is like this. Given a plant and now we have a pre-designed controller C, we aim to design a new controller C prime having integer coefficients so that the performance of the pre-designed controller is preserved in the sense that the closed-loop transfer function from the reference signal to the plant output is exactly preserved. So in other words, within this figure, uh, here for the for the pre-designed controller, the closed-loop system transfer function is try, and with the new controller, the transfer function is try prime. And we want this try and try prime to be equal while c prime has integer coefficients. And interestingly, this problem can be solved analogously to the previous problem of integer stabilization. Um, Let me show how. Uh, so let's just suppose we have, before that, let's just denote the pre-designed controller like this, where the denominator is DC and um, here are the numerators for the reference signal input and the and also the numerator for Y. And let's suppose that we have polynomials alpha, beta, and gamma that satisfies this equation. Then we can design our new controller like this. And with this new controller, the closed-loop transfer function, uh, the new closed-loop transfer function try prime equals to try, like this. So our previous conversion problem can be reformulated with these polynomials alpha, beta, and gamma. So we want to find these three polynomials such that this upper equation holds, and gamma should be an integer monopolynomial because we want this new controller to have integer coefficients. And for internal stability, alpha should be a short-stable polynomial. And also there is a degree constraint for the causality of this new controller. And this kind of looks similar to the previous problem of integer stabilization. So, to solve this problem, we have a mild assumption that the DC, the denominator of the pre-designed controller, and NP are coprime. And analogously to the previous solution, we first initialize alpha, beta, and gamma such that uh, so that they satisfy this equation, and alpha is sure stable, and the degree constraint is satisfied. However, gamma, we cannot make sure that gamma is an integer polynomial. And it can be expected that we update this alpha, beta, gamma so that gamma eventually becomes an integer polynomial. So at each iteration, we choose a short stable polynomial A and multiply it to both sides of this equation and add add this term to both sides of this equation to um, have this new next step alpha, beta, and gamma. And here, having a closer look at this update of gamma, which is rewritten here, we can also express this polynomial update by the dynamic system we have previously shown. And then the remainder is just the same. So, yes, this is the end of my talk. And to summarize, uh, I have shown that to implement a linear dynamic controller over encrypted data, the controller needs to have an integer state matrix, or for single input, single output systems, just have integer coefficients. And in our recent work, we have shown that for any single input, single output LTI plant, there exists a controller having integer coefficients that stabilizes this given plant. And I have described that it is also possible to convert a given controller to a new controller having integer coefficients while preserving the pre preserving the desired control performance in the sense that the closed loop transfer function is equal. And you can see our paper on archive through this QR code, and it the paper includes these two results. And thank you for listening, and I'm happy to take any questions.